Hi guys, and welcome back to my channel. It's been a while since I've made a, chemistry related video, but I'm excited to kind of restart this channel, and it's going to be going in a little bit of a different direction. So my hope is that in this next year, I'm going to, instead of talking about, chemistry Olympiad topics, I'm going to discuss different papers in, computational chemistry that I find interesting and kind of hopefully simplify what they're talking about and just kind of give a broad overview of the advancements in the field. So the first paper I'm going to start off with is called Reweighted Autoencoded Variational Bayes for Enhanced Sampling, or just simply RAVE. And this paper was written by Professor Pratyush Tiwary and et al. And he's a professor at University of Maryland, and I find his work, very fascinating. What he's doing with pushing the boundaries of enhanced sampling methods. If you haven't heard about enhanced sampling, I would encourage you to watch. Actually, I made another video on umbrella sampling, and that video kind of discusses a little bit more about what is enhanced sampling, what is kind of the traditional Metropolis Hastings Monte Carlo, what's the problems with traditional Monte Carlo simulations or molecular dynamics simulations, and all that sort of good stuff. So I would probably watch that video or, know a little bit before hopping into this one, but I'll still give an introduction. So what is the kind of the challenge of molecular simulations? Well, as we know, traditional molecular dynamics or traditional Monte Carlo struggles with sampling rare events due to high free energy barriers. So if you look at our, classic image of a protein folding in different conformations, there's many different energy minima, right? So these different conformations have fall into different energy minima, but to get from each of these energy minima to the other, there's a huge sort of energy barrier. And to get over that energy barrier is very difficult doing these sort of simulations. Additionally, transitions like protein folding, ligand unbinding, these kind of interesting transitions that we're trying to investigate for, all sorts of purposes may take much longer than the available simulation timescales. So, when you think about our time steps when we're working with molecular dynamics, we're usually, on the order of femtoseconds sometimes, right? It's like what time step are we trying to, change, like update our positions based on? That time step is usually this super small time step. But as you can see in kind of the image on the bottom left, the interesting transitions, right? Protein folding, other stuff like that, that can be like microseconds, which is orders of magnitude more. And you can see the time required on a typical computer can be upwards of many, many years. So how can we kind of improve this enhanced molecular simulations? Well, one way is through enhanced sampling. So let's just talk about the prior enhanced sampling methods, and then we'll talk about what RAVE does. Okay, so you should have seen a little bit of this before, but there's two kind of, I guess, main enhanced sampling methods. One is metadynamics, or another is umbrella sampling. So the idea with metadynamics is as you're kind of sampling these conformations, you kind of bias the potential to places that you sample a ton. So you bias it and you raise the potential energy of the places you sample a ton. It's kind of like filling in sand to this potential energy surface. And that's, if you raise the potential of that area, you're going to lower the probability that you pick it again, right? So you're going to kind of bias towards picking other events that you haven't sampled already. Umbrella sampling uses, is kind of a little bit similar, but you use these you break your reaction coordinate into windows. And I have a whole separate video on this, so I don't want to talk too much about it. And there's other methods that are just ML enhanced methods. So use machine learning to kind of define reaction coordinates or choose reaction coordinates. But you often treat these reaction coordinates and the biasing, and the actual biasing as separate steps. So just to refresh, what is the reaction coordinate? That's like an important kind of variable or something physical, hopefully, that defines, an interesting potential energy landscape. So for example, if I'm looking at a ligand binding or ligand unbinding, maybe it's a distance from the center of the ligand to the protein or whatever it's trying to bind to, right? So some interesting kind of variable that defines some interesting potential energy landscape. So what are the limitations of the methods? Well, there's a manual choice of reaction coordinate, right? So for metadynamics or for umbrella sampling, we have to choose this reaction coordinate that we're sampling along. That's not an easy task. Most of these systems, right? If I'm interested in a protein, it's huge dimensional systems. If a protein has n atoms, each atom has 3 degrees of freedom, right? 3 x, y, and z coordinates. That's 3n dimensions, and I somehow have to reduce that problem to a one-dimensional problem. That's not easy. So if I have to choose the reaction coordinate, that leaves a huge problem, right? So this is inefficient, and most of the time we don't know what these reaction coordinates should be. That's difficult. So how can we kind of discover these reaction coordinates? Let's see. We can try and use machine learning, right? So this is where these things called variational autoencoders comes in. And the idea is that a variational autoencoder says what is the best way to kind of compress high dimensional data to a low dimensional space. So if we look at our image on the right, we have an encoder, right, which takes an input, and you can just think of this like encoder as kind of some black box, and it goes to some middle encoded variable, which we call z, and that's going to be in the space. The space of these z's is called the latent space. So it's the space of the compressed values, we can say. And simultaneously, we're training this decoder, right, which takes our z and tries to map it right back to the same input. So the idea is that the z hopefully encapsulates the input very well while compressing it down to a smaller dimension. So this is kind of what we want, right? In order to get reaction coordinates out of a high dimensional system, we're trying to take a large dimensional problem and reduce it down to maybe a 1 or 2 or whatever, very small dimensional problem. So what is the issue with this? If we're able to train this model, right? Just say we're able to train this model and we can get a one-dimensional z, what is the issue? Well, the reaction coordinate, or the z, that's, the space of z's that's identified by the variational autoencoder, might not actually be physically relevant. And this is actually a really important point. So I'm going to give a key example on the next slide. So here's an example of choosing a reaction coordinate that is not actually physically relevant. So say we have this two-dimensional system, which is kind of shown in the left picture on the bottom, right? We have R1 and R2. We have 2 dimensions. Now, for a reaction coordinate, just say, for example, we just take R1 as our reaction coordinate. So we project out the R2, we just get our reaction coordinate, which is just R1. Now, if we look at our, delta G, I guess, along R1, let's look at the 4 to 2 transition, right? It looks on this image as if the 4 to 2 is a transition state. It looks like there's a minima at 4, a minima at 2, and there's kind of an energy barrier in between, right? It looks like 4 to 2 is a transition state, but if we look at our actual two-dimensional system, we can see that in order for 4 to get to 2, it must go through either 5 or go through 1, right? We can see that in our two-dimensional system, like these nodes on the graph almost. So that's not even a transition state. It's not even a real pathway. So the problem is this reaction coordinate, this R1, right? Going along R1, going from 4 to 2 along R1 means nothing, right? Because for us to go from 4 to 2, we must have gone through 5 or 1. So it kind of feels like we're back to square one, right? How can we reliably actually identify these reaction coordinates that are physically relevant without any information? And that's what RAVE tries to do. So let's go to the next slide and talk about that. Okay, so you're probably asking by now, okay, how does RAVE use these VAEs or variational autoencoders differently? If the reaction coordinates VAEs identify are not physically relevant, how do we bypass this issue? Well, RAVE's key innovation is we don't actually look at the reaction coordinate identified, but instead we look at the probability distribution of the reaction coordinate that is identified. So what does that mean? We're not looking at the Z, the specific Z, right? We are looking at the distribution of Z's that is produced. Okay, so that might be a lot, but hang with me. The idea now is that we optimize a physically relevant reaction coordinate chi. So we have our Z's, right, which is based on the VAE. Now we have chi's. Our chi is built as a function of user-chosen order parameters. So we're building chi as a function of kind of things we know are physically relevant. So these things can be, distances, bond angles, many other things, right? But physical sort of variables. And we now have some chi that is a one-dimensional, a one-dimensional output that is a function of these user-chosen order parameters. And we take our chi and we optimize whatever function so that the distribution of chi is going to approximate the distribution of the latent space, or the distribution of Z's. So we match the distributions. We find the chi, or we find the function, or in RAVE's case, they only looked at a linear combination. So they find the weights of the different user-chosen parameters such that the distribution of chi closely approximates the latent space distribution. And so that's the key thing. We're not actually using Z's as the reaction coordinates. We're using our separate physically relevant chi's as our reaction coordinates, but we're sort of matching these distributions so the Z's and chi's kind of act similarly. And so we do this in an iterative way because now we can run simulations and bias it at the same time. So how does this work? We run a short unbiased simulation. Then we use our VAEs now to take that unbiased simulation data, right, and learn the latent space distribution. So train our VAE now on this data, figure out what our latent space distribution is going to be, update chi via what we call KL divergence minimization. Okay, so this is a way to, I'll talk about this on the next slide. It's kind of math to match the distribution. Then we use the distribution along chi, right? So now we know this chi distribution. Now we can bias further simulations once we know our chi distribution, our reaction coordinate. And then we repeat this kind of cycle until convergence. So then we go back, we use our VAEs to learn the latent space distribution and keep going. So we're kind of biasing while also discovering reaction coordinates, right? So that's the whole key thing, is we're discovering reaction coordinates, biasing, and then repeating, discovering reaction coordinates, biasing, and we keep kind of doing this iteratively until we have some convergence. That's the key part of RAVE, is we're doing these things simultaneously, and we're doing them in an iterative manner, and we're waiting for a convergence to happen. Okay, so I said I would talk a little bit about KL divergence. We're not going to go into it, but the key idea is we're measuring the distance between distributions using KL divergence as a measure of distance between distributions. So this is the actual math behind it on the right. If P of Z, you can just check for mental sanity. If we have P of Z equal to P of chi, so if the probability distributions are exactly the same, right? Then the log term is going to vanish because we're going to have P of Z over P of chi, which is 1 if they're equal, and then log of 1 is 0, and the total sum will be 0. So you can see that the KL divergence, right, will become 0 if these distributions are equal. Okay, so now that in this loop, right, in our iteration, I promised you that we get our chi, we get our reaction coordinate, and then we do the biasing, and then we run the sampling, right? So now that we have our chi, we need to use this to bias and carry out our sampling. And the idea is we want to create the bias potential to encourage sampling rare events, right? That's the whole point of this. So we want, and these rare events are values of the reaction coordinate with low probability. And remember, this bias potential is basically what is going to be added to the original potential. So if the bias potential is high, that means we want to match that with things that have a high probability of happening in our chi, right? In our chi space. Why? Because that means we want to discourage these frequent events from happening in relation to rare events. So if we look at our equation, V bias of chi, you can see that we have, this is basically some constant times log of P. So if the P of chi is high, so if there's a high probability of this specific, reaction coordinate happening, that means we want to bias against it. And that's what we do, right? We raise the V bias will be high. And so we will discourage sampling these frequent events. So after we do this biasing, we then unbias our sampling by basically deleting the bias potential we added, and that can be done very easily. It's the same exact way we do it with umbrella sampling or metadynamics or any of these other methods. Now that we have our bias potential, we can unbias very easily. So this is kind of the key idea, just the key methods of RAVE. Very simple. The idea is we simultaneously look at reaction coordinate and do the biasing at the same time and do this iteration until we have some convergence. So here's just some quick results. They tested this on a 2D and 3D system, as well as another hydrophobic ligand system in water. But I just want to show these two results. Very simple. In the top two images and the bottom left potential energy surfaces in both of these, you can see RAVE basically progressively learning better bias potentials and a better reaction coordinate. So you can see in these images, right? You can see on the top left of each graph, you have the bias potential. And on the red line, you see the reaction coordinate that it's identifying. So you can see that it's slowly learning a reaction coordinate. And in the bottom right image, you can see that RAVE basically finds the delta F between the two wells is 0. And it finds it way faster than the unbiased simulation does find it, right? So if we look at the unbiased MD, the red lines go to 0 much slower, right? It takes way more molecular dynamic steps for these red lines to go to 0 compared to the blue lines. And that's what's key, right? The key thing is that RAVE is much quicker, takes way less steps in order for the simulation to approach the truth, right? So that's what's important about this. Okay, so what are the limitations of RAVE? Well, we still rely on these user supplied, right? We need to still tell RAVE what are the order parameters we want to make a function of. What function should I make it, right? That's all like non-specified. Should it be a linear combination? Should it be something else? Another limitation is that high-dimensional systems are still challenging, right? It's still difficult for a single reaction coordinate to capture all the relevant motions in such a huge system like a protein, right? So it's still a huge problem. And RAVE, what I kind of mentioned a little bit, was like it currently focuses only on linear projections of the order parameters, like weighted linear combinations. But future work is to make, nonlinear or multi-dimensional generalization of this. Overall, what did RAVE do? It unified learning, right, and sampling. A unified learning about the reaction coordinate and sampling. It's identifying meaningful reaction coordinates along with the bias potential construction in one kind of iterative step. It's also distribution-based biasing in the latent space, right? We're not looking at the z's, we're looking at the distribution of z's. And from that, figuring out our reaction coordinate. We saw that there was a faster convergence when compared to traditional, molecular dynamics methods. And it's moving enhanced sampling away from intuition-dependent workflows while still trying to preserve the physically interpretable nature of enhanced sampling. So thank you guys so much. This is my first video on these papers. I hope you enjoyed it, and I'll see you in the next one.